Hey everybody, this is 11E, motion in an elevator. So it says the scenario is a student whose normal weight is 500 newtons, stands on a scale in an elevator and records the scale reading as a function of time. The data are shown in the graph below. So we can see here normal 500 Newton reading of the scale goes up to 700, back down to 500, and then down to 300. You should know, and you can see actually right here at the very end it jumps back up to 500 there with that vertical line. You should know from our work in class that this means that the elevator is accelerating up, and this means that has an upward acceleration, I should say, and this one means that the elevator has a downward acceleration. Let's see what questions that they ask us here on this one. So they say, describe the motion of the elevator for each of the four segments, filling in the table below to represent the directions of position, velocity, and acceleration. Assume that the upward direction is positive, so that's important, and that the elevator starts from rest, so that's also important to know there. So first part, 0 to 5 seconds. What is the acceleration? Well, we have our normal value there, so we know that our acceleration is simply 0. And then it says, is the elevator speeding up, slowing down at constant speed? Well, we know it's at a constant speed because if we have no acceleration, we're at a constant speed, and more specifically, we're at rest because we started at 0. So next part says from 5 to 10 seconds here, what is our value? Well, look, we have an acceleration here, upwards. So we have a positive acceleration. That is why the scale reading is larger. So since we are headed up from rest, that means that we are speeding up and we are moving up as well. So then next part, 10 to 15 seconds. We are back to, if we look here, a normal scale reading. So we're back to 0 acceleration. So 0 acceleration, which means we're back to constant speed, but we are still moving up because we haven't slowed down. We just are no longer accelerating. We're no longer increasing our speed upward. And so then last, the 15 to 20 seconds right here, we can see that we have a negative acceleration because the scale reading is less. So acceleration is negative, which means if we're moving up and we have a negative acceleration, then we are slowing down. But again, we are still moving up. We have not yet had a chance to reach rest. So now let's go back to this for 1 second actually, or here, I'll use this space. And let's develop the Frankenhoff equation from this, because this might be useful going forward on this. So we know that we have the normal force up, that's the scale, minus the force of gravity down, that's the sum of our forces. And so since that's the sum of our forces, we know that equals mass times acceleration. So now if we want to solve for the normal force, which is what the scale reads, we can move the Fg over here. And I'm going to write the Fg as mg. So mg plus ma. And so now let me just factor out the mass so this part becomes a bit clearer. You don't have to do this. But you can see here then that if our acceleration is 0, then this part's gone and we just get mg as our scale reading, our normal weight. But if we have a positive acceleration, this term will be bigger than normal and we will get a bigger scale reading than normal. But if the acceleration is negative, this term will be less than normal and we'll get a scale reading that is less than normal there. All right, so next up, they want us to draw a couple of graphs. The first one they want us to draw is a velocity versus time graph for the whole time there. Now we have on the other graph, if we look back on it, you can see that it goes to 5 and 10 and 15 and 20 seconds down there. So that is our time side of it. And then on our vertical one, let's hold off on that for just a second. I'm going to sketch the shape of the graph, and then I'm going to come, just in case they ask you to do this, I'm going to come back in and fill in the numbers. They didn't say to do that. When they say sketch, you just do the shape. I'm going to go ahead and do the numbers in a little bit in case that problem came up. So we've already discussed that in the first 5 seconds, our acceleration was 0 and we were at rest. So our velocity should just be straight along that line right like that. Then we say here that we for the next 5 seconds, have a positive acceleration, and we are speeding up. So as best I can, I really should have a straight edge here. I'm going to draw my line down like that. That's supposed to be a straight line up to here. Then from 10 to 15 seconds, we have a constant speed. So whatever speed we reached, we stay at that for the next 5 seconds. So bring it over. And then finally, for 15 to 20 seconds, we are slowing down. And since on the graph we slow down for the same amount of time that we sped up, I know that we'll get back to rest there. Now, let's put some numbers on here and let's see how I could figure out each of these values. So in order to put some numbers on there, let's use the third equation here. So, or not the third equation, I'm sorry. Let's use the first equation, and let's actually first figure out what our accelerations would have been numerically. So our first acceleration, let's do this. A equals the sum of the forces over the mass. So on the way up, we know that we have the normal force minus the force of gravity. That's actually for both on the way up and on the way down. So let's plug this in first for on the way up. We know that the normal force was reading 700 newtons. That's the scale. And that the student weighs 500 newtons. And the student's mass, well, if you weigh 500 newtons, your mass must be 50. And so 700 minus 500 is 200. 200 divided by 50 is 4. So we know our acceleration was 4 meters per second squared during this time. Also, what about during the final part? Well, we can use the same idea, but now the scale reading is 300. And so we'll do the exact same thing. 300 minus 500 is negative 200. So we'll just get negative 4 meters per second squared. So in case they asked you for those accelerations, we can find them. Let's also show how we can figure out what these velocities actually are. And to do that, we'll use the first equation. So the velocity is equal to the initial velocity plus the acceleration times time. So our initial velocity is 0, our acceleration is 4, and our time that we accelerate at that is 5, so we will get up to 20 meters per second. So this value right here should be 20 meters per second. And we stay at that. And then because we decelerate at the same rate that we accelerate it, then I, again, know that I'll get back to 0 there. All right, last part here. Let's do another graph. This time, they want us to do a position versus time graph for the same setup. So I know that this will be 5, 10, 15, and 20 seconds again. So again, you just have to sketch the shape of the graph, but I want you, or we're going to figure out what the numbers could actually be here on the side. So first up, the first 5 seconds, remember we're at rest, so it stays there. The next 5 seconds, we are accelerating, so we need to have a curve up. From 10 to 15 seconds, we go a constant speed, so a straight line. And then the last 5 seconds, we decelerate, so we should have a downward curve because of the negative acceleration. Now, how could we actually figure out what all of these values are here? To do that, we would need to use the third equation. So the third equation says, I'm going to write it this way too for this particular one. Our final position is our initial position plus the initial velocity times time plus 1/2 times acceleration times time squared. Okay, so our initial position 0, let's say, so we won't worry about that. Our initial velocity 0, so that's gone. So it's simply 1/2 AT squared to figure out where we are at the end of this accelerating portion of 10 seconds there. So if I plug that in, it's 1/2. Remember, our acceleration is 4, and the time that we accelerate at that is 5 seconds. So 5 squared is 25. 25 times 4 is 100. Half of that is 50. So this would be 50 meters right here. Now, where do we get by the end of this? Let's use this same equation here. So to figure out where we are at the end of that next time. So our position will be, now I'm going to plug in for our initial position for this part. We're already at 50 meters. So our initial velocity now, remember, if we go back to this graph, we are going 20 meters per second at the end of that time. So we've got 20 times 5 seconds is how long we go at that portion. And there is no acceleration in this part right here. So 20 times 5 is 100 plus the initial 50. That puts us at 150 meters. So this is 100 meters here, and that puts us, that's 150 meters right there. And so finally, let's figure out what this last part is. But although we can see it, let's just prove it. The way I've sketched this graph out, this should be 200 meters right here, but let's make sure that that actually comes out that way. Now, to figure out the last part, it's actually useful to use the fourth equation because the final velocity gets back down to 0, remember? We know that. So we'll use the final position is equal to the initial position plus the final velocity times time minus 1/2 at squared. And so that's the fourth equation, remember? The final velocity is 0, so that drops out. So when we go to plug this in, we have our initial 150 meters that we began the problem at minus 1/2 times our acceleration of -4. And then our time is 5 squared. Sorry, that's getting all messy in there. So 5 squared again is 25 times -4 is -100 times 1/2 is -50, but there's another negative there. So the 50 winds up adding to the original 150 and you get 200 meters like we just said there.